Zoom land as well. Welcome. So we're here for Ty's honors thesis defense. And I just want to mention that, ASU gets really great students, particularly our Barrett students are as good as any students anywhere in the world. And Ty is a great example of that. I just want to mention a couple of things if my little buttons won't work here. Probably because it's not. There we go. I can't handle technology, but Ty will do better. So Ty has been a space grant intern a couple times. He's been an excellent undergraduate teaching assistant. He's the current president of this undergraduate student council. I believe he's one of the founding members of that as well. He's also currently the president of Geo Club, and we're about to lose him off to Baylor University. So that's we tried to get Ty to stay here because he's so awesome, but it's great. Baylor will, his opportunities there are going to combine the field work, the SED strat, and the paleo, the emo stuff. So that's going to be a great opportunity. So you can see some more. I just want to throw some pictures of Ty in the field, out there driving on some interesting roads. We actually had some rain, and just studying across the overview there down in the Safford Basin. A lot of detailed work, a lot of painstaking time looking at the sediments, getting around to places we can get outcrops, and also some drone work. And it took me forever to fly a drone where I had some confidence I wasn't going to crash it. And Ty was just flying like, and going real close to some outcrops. Like, okay, we spent a lot on that drone. And then also Ty was able to come out, help us out in Hawaii this last summer, which was excellent. Ty was a great field assistant everywhere, every way, always a positive, helpful attitude. And if we had any weird combination of leftovers, Ty would eat it for lunch. Including the day when I thought he knew I was joking and I suggested the most disgusting combination I could think of, and he ate it. That one he did not enjoy. But we had a great time out there. It was really great. Ty could come with us. And with that, I will stop and let's hear from Ty.
Thank you, Colin. Oh, this is a big audience.
Everyone's watching.
Yeah. Okay, so should I sit or stand? You guys whatever you feel most comfortable. All right, happy Earth Day, everybody.
Happy Earth Day.
It's kind of a coincidence. I didn't plan this to be Earth Day, but it's a good day to celebrate the Earth, the landscapes that we see on the Earth, and maybe learn a bit about how we can interpret those landscapes. And the sedimentary deposits, of course, are the best thing on Earth. It's been an honor to work these past 2 years with Helen and with guidance from Arjun and Dwayne, with everybody else in our research group that has helped me, other people who helped me in the field, and it's been a great opportunity to learn, and to test my skills, and to just do something I think is really cool. Now, on to some background. So. Geologic setting, broadly, Arizona. Starting around 27 million years ago in the Oligocene, Arizona started undergoing southwest-oriented crustal extension. Okay. And this is what creates the 3 physiographic provinces that Arizona has today. So these 3 provinces are, an extension, of course, southwest. First, the Colorado Plateau is high and flat. In the middle is the transition zone. It's this really high mountainous, high relief area. And then in the south, we have basin and range. I love the basin and range. And it's low elevation, but there's high relief because there's a series of mountain ranges and basins that are parallel. And this extension first happened along low-angle detachment faults. These myelinic shear zones essentially created metamorphic core complexes, not as important to know the details of. And then there was a second period of extension from around 15 to 5 million years ago, where these high-angle normal faults broke the crust up further into these mountain ranges and basins. And this is what creates the basin and range topography that we know of southern Arizona for. We're currently standing in a basin, And if you look anywhere around us, you can see mountain ranges. So it's really an important part of Arizona, southern Arizona specifically. And during and after these tectonics, this faulting, sediments are depositing within these basins. And that's the best part, is the sediments. Right? So after tectonic ends, the basins keep filling with sediment, and eventually, originally they are individually internally drained. They're not connected to each other, but then they integrate. And then you get river systems like the Gila River and the Salt River that then start to evacuate sedimentary material and erode the deposits that were deposited. Now, if we look at Arizona again, we zoom into this southeastern part here is the study area that we're looking at. These are the Pennsylvania Mountains. These are a metamorphic core complex, so that early period of extension creates this mountain shear zone, as I mentioned, but the modern range that we see today is created by that high angle normal faulting in the second period of extension. These are a great example of the Sky Islands because they are so high in elevation that they are a different climate than everything around it. And there's a legacy of work in these mountains from Kellen and Arjun and their students over many years. They've looked at this place for examples of landscape evolution. They look at erosion and how erosion varies with tectonics or climate. And they've always, whenever you go out there, you see this landscape. And you see all of these dissected mesas. There's lower channels in between, but there's higher fan remnants near the range. And this sort of begs the question, how did this happen? If we sort of zoom in, we can sort of see that these mesas seem to be bulkily made of these fine-grained sediments, and they're capped with a thin layer of gravels, these boulders. And these fan surfaces cap nearly everything in the basin, and there's different levels of these surfaces, which usually means there's different ages, right? And my job here is to sort of look at those patterns and see what's the explanation for that. Is it related to climate or tectonics, like the previous work has done? But I'm looking specifically at how we can explore these through the sedimentary deposits instead of things like the channels that are eroding into the bedrock. And now there's two hypotheses that we focused on for this project. They're two extremes. So the one is a completely climate-driven, and in this case, that first one up there, you see a completely vertical change, so that there was only fine-grained sediments depositing. Something changes in the production of sediment, and then you have a bunch of boulders. It's an extreme. It's probably not accurate as to how something might happen, but it's good for testing these ideas. And the second hypothesis here is instead of a vertical change, there is a lateral change. There's a shift in these facies where the boulders and the fine-grained sediments are depositing at the same time, and they're sort of moving back and forth, and something happens at the very end to push the gravels out over the top of the rest of the basin. And the key here is, how do we test this? Well, we look for what's different, right? And then we can go from there.
You didn't admit you don't have the power. Yes. Eli's just trying to get it real quick.
Okay. We look for what's different, and that happens to be the fact that there is those gravels lower in the section in the second hypothesis, and they're laterally adjacent to those fine deposits. So that's what we're going to look for to sort of test this hypothesis. And as I mentioned, those are our objectives, is to look for those evidence of the gravels lower in the section and laterally adjacent. We're also going to be mapping the different fan surfaces, these different ages, sort of see what we can tell about the incision as this basin erodes out. And then the final product would be a geologic map of what we interpret to be these sedimentary deposits. Now, as for how we did this, it starts with planning, right? Now, first we consult previous geologic maps. There are plenty. There's actually one that was just published in December, and I'll talk about that later because it's sort of like a useful comparison to ours. But we look at the topographic data. We got some LiDAR DEMs of multiple resolutions. And we can produce hillshades, slope maps, and 3D surfaces to look at in ArcGIS Pro. And it's useful to sort of see, okay, what are the patterns you can see? And then specifically what we want to do is locate exposures of the sediment. This is important because if you're just on the side of one of these mesas, it might look like it's completely made of boulders. However, this is a trick. This is just a lag colluvial deposit, right? So if you actually get a good exposure, you can see that there's only a few meters max of those boulder deposits on top, and whatever's underneath is completely different. It could be boulder still, but it also could be completely mud or sand. So it's important to find these exposures to sort of reveal the true sedimentary nature. In order to do this, we used a slope map, which is basically, it's highlighting areas with high slope, which is indicative exposure. So the most successful threshold we used was a slope of 35 degrees. This was tweaked with field observations, and this seemed to be the most successful for our uses. These exposures typically were cliff faces, landslide scarps, road cuts, and gullies. Road cuts were particularly useful because they sort of just cut through the landscape, so it's good to see what's underneath. A good example of that is that landslide scarp in the bottom right there. It's kind of hard to see, but it's lit up in red, so it's a good representation of how our methods worked. And then we'd go through and mark all these locations that looked like they're for sure good exposures. And we create a good field itinerary because we only have limited time in the field. It costs money to camp there, spend food, spend time and gas out there, so we're trying to be efficient. We rank the priority of these sites by have we been there before? Does it seem like it's going to be exposure for sure? And then we also factor in if it's accessible or not. Is there a road that runs through there? Is there private property blocking it? And then we sort of come up with this list of targets, and we come up with routes to get there. An example of this is a field plan. This is from January, our last major field work. All those blue lines are the proposed routes that I traced. Each pin is a different exposure I marked. And out of all of these, I think we made it to probably all but 2 or 3 of the routes here. So by the end of the 2-year period, I feel like we got pretty efficient at planning and getting the fieldwork done. The fieldwork itself is qualitative observation. We look at the sedimentological characteristics, and this includes grain size, of course, is the most important thing, but we look for sedimentary structures that provide insight into what kind of depositional environment the facies. So is it a stream deposit, a lacustrine facies, or is it alluvial fan? And we do this on foot, by truck, through binoculars, and we do a lot of drone work as well for when we can't exactly go to find up to the outcrop. It's on a cliff or something. We build a patchwork of these observations, and from this patchwork we can sort of infer the geometry of these deposits and the stratigraphic architecture, and then from those interpolate the contacts between them to sort of draw the lines on the map and then fill in the rest, right? So, and this was aided by topographic analysis. I'll cover that in the results, but yeah, and I think, just wanted to highlight some field photos because that's one of the best parts of field work, right? And for the last 2 years, we've been out there a few times, and I always try and get good selfies. Specifically, I really enjoyed the droney in the bottom left there, the taken from the drone. But yeah, field work is fun for me at least. So, on to results. Okay, so when we look at our observations, we use the Field Notes app. It links directly to ArcGIS Online. So anytime we reach an outcrop or see something on a mark, we can put a GPS point down. It links the notes and the photos to that point, and then we upload it. And then later we go through that and characterize each one of those by what facies it is. Each one of these points is an observation we made, and then the color corresponds to the type of sedimentary depositional environment. And there's 3 main basin fill facies that we encountered, and these are not necessarily new observations. They're just what we saw, and they have been seen before, but it's good for us to learn through this. So the first were the fine-grained basin fill. This is those muds and sands that are the bulk of those accepted mesas at the start. The lacustrine muds, these are lake beds, usually well bedded, so there's pretty good stratigraphy there. A lot of times they're gray or green, so possibly anoxic conditions in the lacustrine environment. And then there's a lot of root and stick casts, pretty common. And then there's fluvial deltaic sands and silts, so this is like streams running into the lake or running towards the axial stream system. These are usually just a medium sand or fine sand, but in areas that can get pebbly. or silty. When it's silty, it's usually massive, but otherwise it's fairly well bedded. And there's a lot of trough cross bedding. So there's a good evidence of flow happening. Most of the flow is toward the north or northwest. And there's also lateral accretion surfaces, which are evidence of sort of small meandering stream deposits. And it's important to note that intercalation of these facies were observed, meaning that these two were not completely separated spatially. They're sort of interacting with each other. The margins of the lake are shifting back and forth. Now the next are these proximal alluvial fan deposits. These are huge boulder conglomerates. I'm sort of grouping those gravel caps into this, but it also, we found, are separate from the gravel caps lower in the section. There are alluvial fan deposits. These are cobbled to boulder size. Areas can have finer grains, but generally they're pretty massive and large grain. And they don't often have stratification or imbrication, so we can't always tell the flow direction or like different events of deposition. But they are class supported, which supports more of a fluvial deposition rather than strictly debris flow. And we found that these highest gravel caps, as I mentioned, correlates to these older alluvial fan remnants. So the underlying deposits are part of this basin fill sequence, and then the top alluvial fan remnant seems to move out towards those highest gravel caps, and I'll cover that in the discussion. And then the most interesting part to me is this facies transition zone. So we actually see a broad area where you have both the fan gravels and the fine grained facies interfingering and interbedding with each other. We first saw this in Fry Mesa, which is like this huge fan remnant, has a steep face, and you can see this exposure on the top there. There's boulder like stringers in with fine sands and mud. But this also occurs on a smaller scale in other areas, so it's not always the huge boulder deposits. There's also smaller gravel deposits as well. And these gravel deposits are similar to the alluvial fan facies. They're class supported. Sometimes they have this inverse grading to them, which also suggests more of a flooding or debris flow, which bolsters our identification of this as alluvial fan gravels. And this facies transition zone acts as sort of like a gradational contact between these two facies. And we are able to map it almost across the entire basin. There's just a few small areas where we had to infer where it was, but other than that, it seems like it's represented across the range. And then an important part beyond fieldwork was topographic analysis of erosional morphologies. So each of these deposits had a unique topographic signature that when they erode, they have a certain characteristic. So for example, the fine-grained basin fill had these badlands-like slopes and these lumpy mound-like remnant terraces. So that bottom left picture there is the top part is that gravel cap, but then everything around it are these lumpy remnant terraces. So whenever we saw that, it's pretty convincing that that's fine-grained material. The facies transition zone, so this is the coarse and the fine together, often had this ledge and bench topography, which we field truth this represents differential erosion of the fine and coarse layers. The gravel-rich deposits, like the alluvial fan deposits, and the gravel caps are usually smooth or lobe-like, but these are not always diagnostic. We can't really differentiate between the different fan surfaces just based on the erosional morphology. We have to rely on other means for that. And all of these, including with the field observations, helped us to draw those contacts more accurately on the geologic map. Oh, and there's an illustration of the differential erosion here. So, and then we mapped the different fan surfaces. This was mainly done on either in the field just by like relative, we can tell that they're different elevation surfaces, so they must be different ages. But also in ArcGIS Pro, it's really useful to have a 3D surface of the landscape that I can compare the different levels of the surfaces and then also just click and then see the actual elevation. We map at least 6 of these lower fan surfaces in the highest basin floor fan remnants. There's probably more than this, we just grouped it into 6. a bunch of the lower surfaces, the lowest, youngest ones we grouped together because I didn't think it was necessarily useful for us to differentiate those. Also, when it was a bit difficult to tell just by relative elevation, I created elevation profiles along these fan surfaces to sort of compare, okay, what's the slope here? Does it make sense with what was happening with other surfaces of what I think is the same age? And this sort of suggests that each of these fan surfaces was deposited as the landscape was eroded because the underlying deposits are intact. There's sort of a disconformity between the capping fan gravels and the underlying basin fill. Some of the section is removed in the lower surfaces, but below that, it's intact. And this is the final geologic map that I came up with. So I'm covering most of the range because the bedrock was not differentiated here, but each of these colors represents a different sedimentary unit. And I broke them up mainly by these facies zones that I mentioned. So the red, near the range, that's the coarse-grained alluvial fan. In between, that orange is that facies transition zone, and everything from Frying Mesa North, Frying Mesa, can you see my mouse here? Right there, that's Frying Mesa, this is this huge fan remnant. That and everything to the left of that, we had pretty good evidence of this facies transition zone. To the south, it was a bit tricky, but we inferred that it was there. And then the yellow are those fine-grained basin fill further up. And everything else is a fan surface that's younger than that. So they're a bit difficult to differentiate just by the color. I didn't have that many options in the color settings, but that white, broad, low-level surface is the youngest stuff that we all grouped together. And then there's a sequence of these decreasing elevation surfaces, Q1 through Q6 is what I meant them as. Now discussion. So revisiting those two hypotheses from the start. So remember, the first hypothesis is this climate-driven one. It's completely vertical. The second one is this side-to-side lateral adjacency hypothesis. And we're looking for that evidence of lateral adjacency. This is exactly what we saw. So that facies transition zone is evidence of that lateral adjacency between the alluvial fan, the facies, and the fine-grained facies. And the fact that they're lateral necessitates that they are adjacent, or that they're coeval, so they're depositing at the same time, right? And then since the highest gravel cap is correlative with the alluvial fan deposits, the best explanation we can come up with is that that cap represents a sudden progradation, so a sudden shift in the facies toward the basin that caps the rest of the basin. And what initially seemed like an upsection change due to possibly climate shift is better fit under something like Walther's law of facies, which is basically saying that any vertical succession of these two different types of sediment is better recorded as shifting of laterally adjacent facies rather than something changing. Now, what caused the fan progradation? This is a bit more speculative, but those small variations in the shifting that record the interbedding in the facies transition zone, those fine and coarse interbeds, I think that those are more reflective of smaller climate variations. So like as precipitation and evaporation vary, the lake level fluctuates. This changed the local base level. And then sediment flux would also vary with this, so it's sort of pushing that facies margin back and forth, creating these interbeds, but they're overall smaller shifts in comparison to the final progradation. I think a good explanation for this would be the end of tectonics. So this is like a sudden shut off, the basin stops dropping out, and then all of a sudden the supply of accommodation space slams stop, and you get this progradation outward. And then this progradation could contribute to the filling of the basin, overtopping of the sill, which leads to the integration of the river, and the heel river starts to erode. So then overall deposition stops, although there's periods of fan aggregation. Now we know from previous work, Arjun, him and his student Matt Jungers dated a bunch of these rocks using cosmogenic nuclides, and we know that incision starts at around 2 million years old. So by then, deposition has to stop. So We know that that's one constraint on this. Since then, there's been a lot of incision, at least 150 meters, probably more than that. And these fan surfaces represent periods of aggradation. So, overall, the landscape is eroding, but whenever sediment flux overloads these channels with sediment more than they can carry, they sort of build up into these fan surfaces, and then they start to cut again as soon as there's enough capacity to transport and start eroding the deposits again. And this leaves this series of fan surfaces and gravel caps which lie disconformably on the underlying basin film. Now, looking back at the landscape, you can sort of, initially just coming out there for the first time, I was sort of like, oh, this is kind of cool, I guess. Like, I don't know, these mesas are interesting, but then if you spend time in a place, you sort of get connected to that place, you learn more things about it, and suddenly something that just was kind of cool has this deep, million-years-old history of this deposition. Something big happens, and then all of a sudden, all of this material starts getting washed away by, stream erosion and things like that. It's just really cool to me. And acknowledgements, of course. This was funded by Space Grant and NSF. But of course, I need to thank Kellen the most. Thank you for guiding me and mentoring me over the last 2 years. Thank you to Arjun and Dwayne for offering guidance. I know we didn't have any official meetings as many times as I would have hoped, but we talked a lot, we shared ideas. Thank you to Emily Godin for offering assistance and support in the field and out of the field, as well as Emily Speckman, I know you're online, and Cambria, and everybody else who helped me in the field. I'm just really appreciative of everybody, and everybody in my personal life who supported me along the way as well. Thank you.
Now's the time we can just invite any questions, anything you guys are interested in from the general audience. Online as well. I will monitor the chat.
Did you have a field site that had all of the surfaces in view? I saw like you were missing Q1 and Q5 from the one you showed us. Was that the most complete, or did you have anywhere? On your map, it didn't look like I saw anywhere there was a whole section.
No, not really. This was the best example I had of those different ages.
Mm-hmm.
A lot of times they were sort of separated across the range, and I compared them by elevation. They were clearly different, but there wasn't like one, like Q5, for example. There's only like one area that has that.
Yeah, so why do you think it's not here then?
I would think that it's due to some sort of like, it could be due to like, if the fan aggradation is based on sediment flux, maybe there's something local that causes an increased sediment flux there that degrades there, and other places it's not preserved as much due to increased erosion there, or it could also just be a coincidence that it's eroded away.
So, not preserved, or like it was there and like got eroded, or it's just never was there? Do you think?
I would lean towards it was there and it got eroded away. Yeah.
Thank you.
Question, you guys gotta have some questions. Well, I'll ask, Daniel Chupik has one. I'll read it, I guess. Well, first he says, beautiful fan services and great maps. But he wants to know, are there any tephras in the lacustrine mudstones? So do you know whether they're Pleistocene or the younger? Do you know the age of the sediments?
Yes, there are tephras in the lacustrine facies. I think it's further north in the basin, usually. And they have been dated. I think they're mainly Pliocene in age. There is Miocene deposits below. I don't think any of the Miocene deposits are exposed in our localized field area. Maybe other places in the extended basin, like towards St. Carlos there might be or something. As far as I know, there's no Miocene deposits exposed here on the range.
Cool. Aaron has a question for you.
Yes.
Really good talk. It was really amazing to see the maps that you've made.
Thank you.
One question that I had about the custom deposits were, how do they change as you go kind of away from the transition zone? Is there any kind of like sedimentary structure change?
You know, I feel like the areas, and we focused mainly on the range front, so we didn't go that far away, and a lot of times the sediments weren't preserved further away, but I think it seems like the deposits that were further away were less well bedded, if that makes sense. I don't know if that was also on the southernmost side, so maybe that was due to like, it was closer to the stream deposits, which might have disturbed the laminations there, but I didn't notice any overall like scheme of change, if that makes sense.
I got another question. Do you have any like speculations on changes in sedimentation rates during the deposits of these different fan surfaces that you've been seeing?
Yeah, so it seems like the earlier fan surfaces are much like, there's a greater difference in elevation between the higher fan surfaces and the lower ones. The lower surfaces like Q4 through Q6 are just barely differentiable based on the elevation. So it seems like there's much less aggradation going on later. I would think that means that there's a lower sedimentation rate, right? So perhaps early after incision starts, there's a lot of production of sediment still from the uplift of the range, and I guess it could also be climate induced, right? But it seems like sedimentation rate decreases as it goes on.
Okay, we have a couple more online, and then we'll continue, Emily. Emily Speckman wants you to go back to the erosional morphology slide and elaborate on the diagram with the red lines.
Yes. Okay. So this is a quick sketch I made, but in the ledge and bench topography,
Can you use places to show people where the ledges and benches are in the wide army?
oh my gosh, I wish I knew that. Okay. So the ledges and benches here in the topography are pretty pronounced, especially in the 1 meter resolution LiDAR. On our actual field notes app, I only had I think it was the 10 meter resolution, and you could barely see it at all. So it's pretty subtle. In the landscape itself, it's also subtle, so like we didn't see it other than in the LiDAR. But then when we went in to investigate it based on what I saw here, we were able to notice, especially comparing to what strata were exposed in the gullies compared to where these should be, it looks something like this. So these really gravel-rich, coarse deposits are harder to erode, so they sort of form ledges. They're cliff formers. And then the finer grain stuff, which is either mud or sand, either way, it was easier to erode, so it formed these slopes instead. So those are the flatter benches on top of the ledges.
Yeah, I just want to say that's super cool, and Ty noticed that completely on his own. You rarely see that in sort of hill slopes, and so easy to miss in the field. We had to hunt. You can see the road that we drove on to confirm these things, but anyway, it was really helpful to realize that. Well, Specky will let us know if that was not a satisfying answer. Let's go here, back to Emily. We've got a couple more online too.
My question is, since you didn't get too much into like limitations or future research, if you were to continue this work, or if you were to make improvements, what would you do and why would you do it? Knowing what you know now.
I mean, ideally, like it'd be great to sample and get ages for more of these sediments, because I didn't cover it. I sort of ran out of time, but like a limitation on my interpretation of the tectonics thing is that the incision occurs around 2 million, but tectonics ends by 5 million at least. So there's sort of this 3 million year gap that's sort of like, okay, is it just a delayed response to the tectonics? Is like what's happening there in that 3 million year time? Is there a period of non-deposition? So like, it would be great to get ages, sort of constrain, okay, when exactly does this propagation occur in relation to the earlier segmentation? I mean, it'd also be nice to measure the section. It's not as easy because of the lack of exposure, but if possible, it'd be nice to quantify the different intervents and then sort of measure exactly where each one goes. But
And one of the proposals that we had put together was to date the finer grained stuff with magnetosstratigraphy and connect it with oxygen isotopes and carbon to back up the paleoclimate signature. So it was to constrain the climate history of these deposits to get a finer time scale on it. That's what Kai is presenting.
So perhaps related to this, or related to this, Eli, A1 to apologize for being able to get in late, and thought you had amazing figures. And he wanted to ask if you could explain more how you determined the age sequence of those quaternary surfaces. Like, was that based on previous literature or some other type of analysis?
so these were sort of maps, especially in the most recent map from December. Oh, and I forgot to mention this. The map that the AZGS published in December 2025, a lot of their interpretations match what I interpreted, so that's sort of like a bonus to simplifying what I think. But when it comes to mapping these, I tried not to be biased by previous maps. It's sort of like just go with what I observed, what can I go from there. Some of these, there's a few things in the field that we like use a rangefinder, we could see, okay, this one's definitely higher. So like, I don't think I have a picture of it here, but we could see across like a canyon, it's like that surface is definitely higher than what we're standing. And in that case, you know, we mark down in the notes. I know for sure these are two different ages, but it was mainly just in ArcGIS Pro, staring at the damn 3 surface for like too long, and just comparing, okay, can I like get a weird look at this? Is it the same? And if they're slightly different, is that just a look, like is that actually a different surface, or is it just a different thing that's building up? But I think the thing that helped the most in distinguishing these was like getting a profile of each of these surfaces. So like, if these two ones, I think they're different, but they look similar, I draw a profile and compare the profiles and be like, okay, it looks similar, but like they're clearly different in profiles. So like one has a different slope or something, or like one starts at a lower elevation but then intersected, like, yeah, stuff like that. Yeah.
Which you were fortunate to have the high resolution LiDAR
Yes.
data.
Yes.
Because we didn't have that in our VIPA, and that made it trickier in our VIPA. So it's great, because the way that you described it is just exactly the best you can do.
All right, any last questions? All right, let's